All right, hello everyone. Thank you for attending today's webinar, 5G mmWave Disrupting or Disappointing, presented by Casa Systems. I'm Kevin Gray, publisher of Fierce Wireless, and I'll be moderating this webinar. Our speakers today are Ian Gillett, founder and president of IGR, and Steve Collins, senior VP of Access Devices at Casa Systems. You can read their full bios on the left side of your window by selecting the Speakers tab. Now, just a few technical notes before we begin. The webcast is being streamed through your computer, so there is no dial-in number. For the best audio quality, please make sure your volume is up. This webinar is being recorded and will be available on demand within 24 hours after the event. Time permitting, we will follow the presentations with a Q&A session, so please submit your questions using the Questions and Answers tab on the left side of your screen. Okay, now let's go ahead and get things started. Ian, please go ahead.
Okay, thank you, Kevin, and good morning, good afternoon, everybody. Thank you for joining us today. I'm going to do a quick introduction to the fixed wireless 5G discussion today. Then I'm going to hand off to Steve Collins from Casa Systems, who's going to dive into more of the technology and more of the technical discussion there of how we deploy 5G fixed wireless in the millimeter wave. So what you see in front of you is our view of how the 5G world will look in the next 5 to 10 years. And as you can see, there's a lot of words on here. There's a lot of pictures. Everything at this point is 5G, both in the local area and on the macro cells as well. The important thing is, I think a lot of people think that 5G is just millimeter wave, or it's just this, or it's just that. In reality, 5G is going to cover everything that we now have with LTE and the lower bands, as well as the new millimeter wave bands as well. It'll be indoor, it'll be outdoor, it'll be for enterprise, it'll be for mobile operators. So what we've done here is kind of show all the different scenarios, different applications, and I'm not going to go through all of this. We could spend all the time doing that. But if you just look over on the right-hand side, you see a yellow area, shaded area with home in it. There's a picture of 2 little houses, an autonomous vehicle sitting outside, and a 5G small cell. This really is a high-density, high-capacity area where we've got 5G here providing broadband to the home. And this is really, as we get further into the discussion today, you'll see this is a great application for fixed wireless access with 5G. Houses don't move, so fixed wireless works really well. And of course, now we're all working from home with the pandemic. The importance of broadband becomes is even more critical. It's not just for watching movies; it's also for work as well as entertainment, but also contacting emergency services, maybe having a telemedicine call with your doctor, et cetera, et cetera. So it becomes very important. The other ones draw attention to, and Steve will talk a little bit more about this in his presentation as well, but if you look down the bottom left, you'll see manufacturing and logistics. 5G can also be deployed inside a manufacturing plant, a factory. It can be used high bandwidth, low latency connections used for controlling autonomous vehicles, robotics, machine tools. One of the big appeals to the manufacturing world is that they can reconfigure the production line without having to move the fiber optics, which is very expensive. Using a wireless connection, you can just move the machine tools, and of course, those connections follow with it. So these two we really see with millimeter wave. Some of the others will see millimeter wave as well. In the stadium, for example, in some of the Class A commercial space, we'll also see some of the 6 gigahertz spectrum as well, depending on the application and depending on the vertical. So on the next slide, let's talk about some of the cost factors involved for fixed wireless access. And really this builds into what is the ideal location, if you like, for fixed wireless. So firstly, the first question is, well, am I going to upgrade to mobility, or am I just looking to provide fixed wireless? If you need to upgrade to mobility, it's going to change the architecture, it's going to change the cost basis for that. Signal propagation becomes very important when we're talking about millimeter wave. And again, Steve is going to get into this in some detail in his presentation and talk about some of the work that's been done recently to extend the signal for millimeter wave. Obviously, the amount of propagation you get is going to determine the number of cells is needed to cover a given area. the availability of fiber locally. On the pole where the radio is mounted for fixed wireless, we are going to need fiber to feed that. So is fiber already in the area? Is it in the neighborhood? Can we attach to it easily, et cetera, becomes a cost factor. Next one is, well, what sort of speed do you want to deliver? Again, Steve's going to talk a little bit about this and give you some case studies. But the fastest speeds you want to deliver are going to need more spectrum and or a higher cell density, which is going to drive the cost. Next one is, well, we've got to put some CPE, some consumer equipment there into the home to connect the rest of the home. How's that going to happen? Is it going to be attached to the window? Is it something that has to be mounted on the roof? Do we have to roll a truck for that? And of course, what end user devices are we going to support? Can we just use Wi-Fi within the home, or is it a dedicated device, which of course will be more expensive? The next one is the height of the pole or the tower that's needed to provide the coverage. Basically, if the higher we go, the more expensive it gets. We may have to put our own tower up, for example, or can we use a local pole that's already existing? And then also, what sort of redundancy do we want to provide for reliable service? As I said, more people are relying on their broadband these days. So really, what sort of, do we have to have backup radios? How are we going to do that? What about backup power, battery support, et cetera, et cetera? All those things can drive the cost. So when we look at the fixed wireless market in the next slide, this is kind of a traditional view of the markets that, and some of the things you need. And again, as I introduce over to Steve in a second, he's going to talk about how we can use technology to address some of these things to increase the market availability. So firstly, we need obviously good geography or topography. Flatter areas work better than hilly areas. The next one is limited foliage or trees. Big leaves on trees, especially in wet areas, tend to block the signal. And then also we need to look at population density. We want enough homes in an area to make it worthwhile to actually deploy the system. But if it's too dense, then we may be better off with putting a fiber in there. If there's not enough homes, frankly, we're just not going to be able to cover enough homes to make it economically feasible. We also want some socioeconomic, those criteria for high penetration of broadband use. Frankly, we've got to have the households are able and willing to pay for higher bandwidth service. Also, we find that if there's fiber already in a given area, it may not be a good fit for fixed wireless. If the fiber service is there, they've already got fiber to the home and it's reliable, then is it really worth putting in fixed wireless? Do we need the competitive situation? Having limited broadband competitive choice is a good one, though. A good example is my neighborhood. I've got a choice of 2 providers in my neighborhood, both with speeds that are frankly not that good. I would love fixed wireless in my neighborhood to provide a third option, and actually a higher bandwidth option that we can currently get. And I also fall into that next one is limited broadband speeds available. Finally, the poor perception of the incumbent ISP. A lot of the ISPs have been around for some time. Some have better customer relationships than others. And so we really have to see, you have to look at the area and say, is it worth going into those areas? So all these factors come into is how big is the addressable market for fixed wireless in a given area. Obviously, if we have manufacturing in there, that's more of a private network situation. And certainly as we look at things like foliage, the population densities, the propagation of the signal, all those types of things are things that the technology can address. So with that, I'm going to hand over to Steve Collins, who's Senior VP of Access Devices for Casa Systems. Steve's going to kind of walk through the technology of mmWave for fixed wireless access, and then we'll have time for questions at the end. Steve, over to you.
Great. Thank you, Ian. Thanks for the introduction. So good morning, good afternoon, everyone. Thanks for your time today. Much appreciated. So today I'm going to talk about particularly the mmWave use case for fixed wireless access. And you may hear me use some terms interchangeably today on the call, FR1, frequency range 1. If I say that, I'm referring to sub-6 frequency. If it's FR2, I'm referring to millimeter wave, but I'll try and use the term millimeter wave if I can, just to have some consistency through to the presentation. So we've heard about the 5G market there from Ian, and there's lots of applications there, as you can see, lots of different use cases. But right now, in terms of what is getting a lot of attention, the differences between the sub-6 and the millimeter wave frequency spectrum really is driving a lot of different use cases and the initial rollout of services that we're seeing on 5G networks around the world. Things like fast speeds, gigabit speeds, more capacity, low latency. These are terms that are thrown around a lot. Fixed wireless allegedly can have some fiber equivalent type speeds. So how real is that? And I'm going to dive into the millimeter wave use case because there really are some challenges around that I believe are being solved, particularly with some announcements this year. Before I get started on the use cases and the devices, let me just take a quick step back to talk about the spectrum assets. And just to set the scene, I often refer to the spectrum bandwidth or the amount of channel bandwidth that's allocated to a service as an analogy of a freeway or a road. And if you have a look at the screen here, you can see some roads of different sizes, and the one on the right-hand side is clearly going to have a lot more traffic, a lot more cars and trucks that can go down the road because of the parallel nature of the extra lanes. And that's very similar to the channel bandwidth that's allocated to a service. If you have a frequency that the service runs on, so it could be sub-6 or it could be millimeter wave, that's interesting, but it's the amount of channel bandwidth, the width of the channel, that really dictates how much performance you can get out of a system. So on the left-hand side, the typical 4G channel bandwidths between 10 and 40 megahertz, they're kind of standard road for today. If you then aggregate those services and you have multiple channels, you can have 40 to 100 megahertz of channel bandwidth assigned, and you can have much more traffic go down that in parallel. But if you're looking at 5G, millimeter wave, FR2, you can have hundreds of megahertz of channel bandwidth assigned, and therefore you can have lots and lots of cars go down those roads in parallel. And that's pretty much how we're getting to the speeds that are being advertised for gigabit services. We're going to have lots and lots of channel bandwidth assigned, and that will then allow for a fantastic service, provided you can get the signal through. So at what frequencies are these different channel bandwidths available? Here on the screen here, I've tried to divide up the different frequencies into different categories. On the left-hand side, on the left-hand column, I've got low band, 700 meg up to 1.8 gig. They are the traditional type frequencies that we had in 3G and 4G services that were really utilized by handsets for mobility applications. Those have stretched a little bit now into the mid-band type areas, and now with 5G, we're starting to touch on high band and ultra-high band services in the FR1 sub-6 space. If you look at some of the rows here, you can see some of the primary use cases that I'm calling out. There obviously are more than these use cases in the real world, but the headline ones, the handset mobility use case tends to be in the lower frequency ranges, mainly because of the propagation and the penetration characteristics of those frequencies. They really are very excellent at that lower frequency, low and mid bands. But as we go up onto the high band and the ultra high band, the propagation and the penetration starts to get quite poor. And when we look at millimeter wave FR2, there is very little propagation and penetration at all, so it becomes a little problem. But the channel bandwidth that I mentioned on the previous slide, this ability to have a wider channel and have more traffic, those low bands and mid bands are very, very cluttered today, largely allocated out to existing incumbents. And so the ability to get more channel bandwidth, particularly in the hundreds of megahertz of channel bandwidth, is very unlikely. And so everyone around the world is trying to make the millimeter wave FR2 band work because there is hundreds of megahertz of channel bandwidth available for allocation up there. And you can get significant download speeds from those channel bandwidths, provided you can get coverage from the network. And that's what I'm going to talk about now. So it's interesting, in the millimeter wave space, there are two modes that are really allocated and specified. Right now, if you look at all the millimeter wave services that you see launched around the world today, and there aren't many, but the ones that are launched are all running NSA or non-standalone mode. And what that means is a lot of the signaling and the admin, if you like, of the 5G connection gets carried out on a sub-6 or FR1 frequency spectrum band. And the mmWave band is used for your traffic, for your customer data. And so it allowed us to launch a mmWave service to market a little bit earlier than had we gone straight for the standalone mode. Now, the NSA mode I've written here is really for incumbent operators, and that's because you need to have those sub-6 bands already allocated and pretty much already in use with your infrastructure. So that the NSA mode was really an advantage for the incumbents to make use of existing resources, existing assets, and then, if you like, add on the mmWave overlay to bring a service to market. Disruptors that are going to come to market, new network operators, may be eyeing off the SA mode, the standalone mode, where it's just mmWave only. And of course, the incumbents can make use of standalone mode as well, and they want to. But the disruptors, the new entrants, will really probably have to wait until standalone mode, unless they're lucky enough to have some existing low-band spectrum or sub-6 spectrum, which is generally unlikely in this market. So I don't expect to see standalone mode type devices in the mmWave space until sometime next year, and most likely prime time in 2022. There is a limitation on chipset silicon availability that will support SA mode in the mmWave space today. And so while the NSA is available and is running, the SA mode will be sometime next year when we'll start to see early devices. But again, my prediction is that 2022 is when we'll see prime time on SA mode for 5G mmWave. And I call that out because one of the things I'm going to be talking about today is the likely disruptors turning up on the market and coming in with innovative new services to supplant or even replace some fibre operations in the region. But it's going to be a little while before the technology is really there to allow those new entrants to come on the scene. So with mmWave, I'm just going to spend a couple of slides talking about the challenges in mmWave because it has had a lot of press and a lot of potentially, I'd say, negative sentiment in the market around how hard it is to make a mmWave service run and operate. I'm just going to touch on some of them and where we've got to on that. So first of all, if you think about a fixed wireless service, the perception has been the only way to make it work is to have an installer come out, strap a unit to the top of your house and point it at a base station. Of course, that will be the best line of sight signal you can have to a home, and that will work. And you can offer some great services that way. But it isn't the only way, but it definitely will be a way to solve the propagation challenges that mmWave have, because it doesn't go very far. It doesn't go through the air very far. It does, when compared to the sub-6 spectrum, it does peter out relatively quickly. So the propagation challenges is real, and the testing that we've done shows that you have to do things very correctly to make it go a longer distance. We did some announcement with Qualcomm and Ericsson just a couple of weeks ago at Casa Systems. We did some long-range press just a couple of weeks ago. I've got some slides on that later in the deck. We have, by adjusting the system and doing some tweaking on the timing, made the signal go a lot further than it was scheduled to go or talked about to go. There was a lot of press talking about mmWave only going a few hundred meters, and nowadays we're seeing the propagation go up into the kilometers. It's still single-digit kilometers, and we saw some 5-kilometer press just come out last week. So it is being solved, but the line of sight conditions do have to be there to go those sort of distances. In addition, there are attenuation losses. So while the distance doesn't go very far, if it hits anything along the way, the attenuation is quite severe, and that can be your handbag, that can be the side of the house, it can be trees, and we're seeing particularly in our testing when the material gets wet. So if it's a tree that has been rained on, that is significantly worse than a dry tree, for example. So the attenuation losses are real as well. These propagation challenges and these attenuation losses make it very, very hard for the operator to then go and model their network in a reliable way, because the signal travel between the G-Node B and the UE is quite variable depending on the environment, and that makes it very challenging from a planning perspective. So what we're seeing is a network that is going to rapidly evolve. And so I've got a picture here on the left-hand side of a device on a rooftop pointing at a G-Node B that's being installed on top of a building. You can make that work, you can point that at the building and all is okay. But what happens as the operator realizes that the network has got some patches here and they need to put some new RAN cells in place? So another cell goes up on the next building, or cells go up on the telegraph poles out the fronts of the buildings. As you can see, you've now got an environment that is rapidly evolving and changing over time quite quickly. Because the cells are small, you need to have user equipment that can dynamically self-select and change between the best available cell as it appears. And that provides a bit of a challenge for some of these fixed wireless systems that have been designed to be quite directional and professionally installed in their nature. So that's something that needs to be considered as well. Last but not least, in our testing of mmWave we've been doing this year, we are seeing reflections play a significant role in the success of providing a service through to an end user. Quite often, the direct line path from UE to G-Node B is not the best path in terms of signal quality and performance. And because the mmWave spectrum is quite reflective when it sees traditional building materials, houses, buildings, even vans parked in the front of the street, these things are effectively a mirror for a mmWave carrier. And quite often, the user equipment can find a much better signal by pointing away from the G-Node B, bouncing off a house across the street, and then up into the G-Node B. Now, these might sound like major problems, but in fact, they're advantages if the device and if the network can make use of them. So it's quite interesting to see how the operators, when they're trying to wrap their heads around these sorts of problems, how they're trying to come up with solutions and how they're trying to plan their network. Because what I'm basically saying is the signal will often find a way to get through to the user equipment, but it finds a way in an unpredictable manner. So how do you then plan for your network? So the answer to that is you need to have an ecosystem that helps you resolve these reflections and these multi-path problems and the evolving network. It needs to have a system and an ecosystem that will dynamically solve these problems for you, so you don't have to solve it at planning time. So in terms of mmWave devices, at Casa Systems, we do focus on fixed wireless as a use case that we're quite convinced is ready for showtime now. And so the different use cases that we're planning for mmWave devices in particular, I'm just going to quickly go through them now. I've divided them into geographical, mainly, type applications, and I'll just go through them quickly. The urban use case on the left-hand side is for high-density living and your typical built-up cities. We are seeing from our testing that the indoor self-installed type device that is sold at a countertop in a shop, taken home by the end user and installed inside the home can work, provided the cell density is small enough, the cells are small enough and there's enough of them around the building. This can be made to work. Some special considerations need to be made onto the location and the placement of the user equipment. Quite often in a home or even an apartment, the Wi-Fi gateway is put in the center of the apartment so that the Wi-Fi signal can propagate throughout the whole apartment evenly. Unfortunately, while that makes sense from a Wi-Fi access point of view, it doesn't make sense for the location of the user equipment for 5G, in particular for mmWave. So we're seeing the location of that indoor UE really being vital to the success of the service delivery to that urban location. So it really has to be right next to the window. The window type does come into it, so certain types of low E coatings on the window do attenuate the signal quite sharply. But I'll go back to my point on the earlier slide about the reflections. We are seeing the mmWave signal finding a way, and it may not come through the window, it may come under the crack in the door and come through to the UE in that way. Very hard to predict that, very hard to instruct the end user to go and test those different locations. So that is a challenge for the self-installation piece, but the urban use case, provided the cell density is high enough, can be made to work. For the suburban use case, it really is network topology dependent, and it depends on how dense the operator decides to build out their network in this location. From my experience, the cell density probably won't be as high as it would be in the real urban environment. So we're seeing a role for outdoor user equipment with some type of light touch professional installation. While it would be nice to have outdoor user equipment that can be self-installed, the mechanics of doing that really don't lend themselves for a safe option there. There has to be some form of securing the outdoor user equipment to the side of the building in a safe way. If it's a multi-story building, you need to be sure that, number one, the owner of the home doesn't put the unit up in a way that is harmful to themselves on a ladder, and likewise, if the device has been put up high and it hasn't been put up properly and then falls off the building and lands on someone, who's liable for that. So the idea of having an outdoor user equipment that is self-installed at this point in time is problematic from a safety perspective and also from a cabling perspective. In some way, you have to get data and power to that outdoor user equipment, and that's challenging to do from a self-install perspective. So our view on this is that there needs to be some form of professional installation, but if the user equipment is smart enough, then that can be, we think, a very light touch to make that work. Indoor user equipment can have a role here for self-installation. Again, that is very much network topology dependent as to whether the density of the cells can be high enough to make that stand up from a business case perspective. I really see the suburban use case as being very similar to the rural use case, which I'm going to cover off in just a couple of talking points time, so I'll come to that. The industrial commercial use case seems to have a lot of merit from our testing and our evaluation. We're looking at lighting up a campus or lighting up a site here with a mmWave signal, and that is very cost effective and very realizable because you have a much more constrained and targeted build out methodology, so you can design your cells and design your rollout to the campus and the building at hand. So mmWave, we think, is very, very well suited to the private 5G and the industrial commercial type rollouts. You can have obviously features like low latency and in-building coverage, and they're things that I think are going to come of age over the next couple of years as we see private 5G really evolve. Just to point out here, the enhanced mobile broadband use case, which is the fast download speed, really is available now and in release 16. So that's really ready to go now. But the end-to-end massive machine or industrial IoT type use case, we don't think is really coming of age just yet with 5G. There are some release 17 features that we think are more relevant for this space. In particular, features coming that will allow the user equipment to become cheaper and more cost-effective for high volume rollouts. The silicon and the user devices are not yet cheap enough, we don't believe, for millions of units to be bought and rolled out around the world because they're still relatively expensive solutions. So I think it's going to be at least 2 years, maybe even 3 years before we see the end-to-end use case, massive machine use case, become cost-effective. It might work now, but it might be very hard to roll out in huge volumes. That's got a little while to go yet. The rural use case for mmWave actually still does stand up in our view. Let me just spend a minute on this, because you think about the rural use case where you want long range. We've shown in the last couple of weeks that long range is now possible over a number of kilometres. But for many operators, a rural use case needs to be 10 or 15 kilometres for a base station cell radius. And that's not going to be possible via mmWave. So we think that a non-standalone type deployment for rural makes a lot of sense. You could have a fixed wireless use case rollout in a rural type area using sub-6 frequencies. And that's a great solution for broadband type speeds that provide coverage to users. You're not going to have fibre rollout to these areas because it costs so much money to run the fibre. But a 3.5 gig type sub-6 5G rollout can run over more than 10 kilometres, and that works very, very well. So if you think of a cell with a radius of 10 kilometres being covered by sub-6 5G, that's a great solution. If it's too good though, you'll have too many users sign up and your cell will get congested, which is the classic problem for fixed wireless. And this is where mmWave can come into its own, because if you have mmWave running on the same base station, you can cover users At the center of the cell, the inner radius of the cell can be covered by mmWave, and at the outer edges of the cell can be covered by the non-standalone 5G sub-6 solution. And that will benefit from the users who are on the sub-6 solution who are further out, because you're taking users off the cell and put them on the mmWave. And it will definitely benefit the users who are on mmWave, because we'll have a fantastic wide bandwidth solution. So the rural use case of having this mixed mode really does have quite a bit of merit if planned correctly. So the super summary of this is fixed wireless really has a role in all of these use cases, provided it's planned and metriced up in the right way. So let's talk about the two types of mmWave transceivers that are available on the market today and what we see them being used for. On the left-hand side of the screen is what I've called low power mmWave transceivers. And these are for your traditional type of devices like a handset or a mobile hotspot. The transmit power for those devices tends to be 23 dBmi. That's pretty standard transmit powers, and they tend to be, from a antenna pattern point of view, relatively omnidirectional. You might have a few transceivers that provide that omnidirectional pattern, but the actual device transmits and receives in all directions, which makes it great for mobile devices, because the handset or the hotspot can be in any orientation, placed on any type of surface in any type of orientation, and it will be able to see the G node B and have a conversation. The problem with an omnidirectional type of device is it tends to be relatively inefficient in terms of a signal going a long way. So these are the type of devices we've seen over the last few years, which are quite limited in terms of the propagation range that they can run over, and you do tend to see some hundreds of meters for those devices for them to work. There are new types of transceivers now on the market, and the device that Casa Systems has spent the last year and a half developing is using some high power solutions. They are transmitting at a much higher power, 44 dBmi, a significantly higher power range there. And I would equate these devices to like a lighthouse. You have a very high power light, and it's got a very focused beam for that light, and you point that focused beam at the G node B. It gets you a much further distance, it gets you a much more range, and it's this type of solution that we've used with Ericsson and Qualcomm to have that press that we put out a couple of weeks ago to get that longer range solution and that long range demo that we did in Australia. So it gets you a much more focused beam, it gets you much more distance, but you still have to get those long distances, the line of sight, because if there's something in the way, then that light beam does not make its way all the way through the G node B. There are some features of the mmWave transceiver that help you with that. There's a bit of beamforming, active beamforming and beam steering there in the solution, but it ends up being around about plus or minus 20 degrees or so on that beam steering. So it allows you to take advantage of some reflections and take advantage of some fine tuning that has to go on from day to day as the environment changes, but it doesn't give you complete 360-degree coverage. Now, if we're talking about 8 component carriers on this solution, we are seeing speeds now capable of 4 gigabits per second if the signal conditions are right. And so you really can get quite a service, provided the beam makes its way through to the end point. So I did want to call out these two power levels, because if you look at fixed wireless, where you won't provide gigabit type speeds, in our mind, the only use case that makes any sense is the high power use case. The low power use case has been interesting to date. It's allowed people to do demos and launch products to the market to date. But really, in terms of a long-term fixed wireless play, it's very limited in its range and also limited in how it can be deployed. So the high power solution, we think, now that it's been launched, is here to stay for the fixed wireless use case, and will be where most operators focus their efforts in our view. So here we have a traditional sort of line drawing of the sort of market that you're trying to light up with a mmWave signal or a fixed wireless signal. Traditionally, when an operator wants to go and plan a network, these items in orange are the different sorts of things that they will sit there and try and plan out. They'll plan the heights of their cell tower. They'll plan what spectrum they're using. They'll look at the propagation constants for that spectrum. They'll look at the radio path loss for those frequencies. And they'll plan out their cell topology, and they'll plan out how they're going to lay out their network. They'll also look at their network infrastructure and what technology they're going to use. This is how we have designed mobile networks for many, many years, 2G, 3G, 4G. You plan the cells, you plan the spectrum, and you plan the bandwidth assigned, and you work it all out. What I'm going to say today is potentially a little bit controversial, but for millimeter wave, I don't think that type of planning works anymore. And the reason being is all those challenges I've been talking about over the last 10 minutes of the propagation problems, the reflections, the changing and the dynamic environment around which the cell operates and the signal operates. It's very hard to assume a ubiquitous coverage using millimeter wave because of all those problems just getting the signal into the home. So now the solution for millimeter wave is to not plan just the base station and the transmission from the base station. You really have to plan all the way through to the CPU or the UE. You have to plan the link. You don't have to plan them one by one. That's probably too cumbersome. We're not going quite that far. But you need to think about the end-to-end service that you're going to be providing to the end user. What type of service are you going to provide? What type of speed do you want to provide? And how do you take that into account? How do you then have, what UE do you service and do you provide to the end user to provide that service? Is it going to be low power UE? Is it going to be high power UE? How's it going to work? All those factors dramatically affect the design of the G node B and the service and where you're going to put that service for the end user. So you've really got to start thinking about this end-to-end link from G node B through to UE as part of this network planning piece. And it's very hard now to just have one ubiquitous network with 100 types of UE that all work on it. It's not really how it's going to work anymore with these different power classes in our view. So it does make it a little bit harder to deploy and plan your millimeter wave service because there's so much to think about. But it is doable. And if people think a broadband to the home offering via wireless is a good idea and a good business case, there's lots of tools available and lots of devices becoming available to facilitate that. So here at Casa Systems, we've been working on the millimeter wave fixed wireless use case really hard over the last, we've been doing fixed wireless in 4G for almost 10 years now, but for millimeter wave, we've been doing a lot of work now over the last 18 months. And 2 weeks ago, we did some PR for the market with a collaboration with Ericsson and Qualcomm, and we completed the world's first high-powered millimeter wave proof of concept testing in Australia using up to 28 gigahertz band spectrum. Here's a picture of the test that we did. As you can see, there's a pump-up mast here with a UE sitting at the top of the mast. The height of that mast is equivalent to the top of the house. So the idea was to emulate having a piece of user equipment installed on the top of the house with a line of sight connection through to the G node B. We have been using the Qualcomm QTM527 high-powered millimeter wave antenna modules for this solution, and the testing we did from that, we really had some quite encouraging results. There was a lot of work that Ericsson and Qualcomm had to do as well around the way the UE and the G node B sent signals to each other. There was a lot of timing problems because the signal was taking a lot longer to go to and from the UE than it was in the low-powered use case because the thing was further away. So it's quite a lot of joint development that went on to make this solution work. The outcomes were quite encouraging. I've got a little slide here which just gives you a super high-level performance graph of what we were testing. On the x-axis here, we've got the distance from the G node B. This is in kilometres. So just to put this in miles, the 3.8 kilometres that we got to in our testing here is about 2.3 miles. And you can see the speeds we had. We started at well over a gig, and by the time we had the 3.8 kilometres, we were down at a bit over 600 megabits per second. So it's still a very substantial throughput and still a good class of service. This testing was done around about 2 months ago, actually, and there's been some extra work that's gone on in the meantime since this testing was done, and some extra timing problems and timing increases that have been made by the team. So there was actually some extra press that came out last week, which showed the signal getting to 5 kilometres, which I was expecting. I'd be surprised if we're going to get much past the 5 kilometre mark. Maybe a little bit more tweaking from that, but not a lot more. And just to reiterate, this is for a line of sight connection from G node B through to the user equipment. But it does show almost an order of magnitude extra range than what the press and what the market's been expecting. A lot of press over the last year talking about 500 meters or so being the maximum range for mmWave, and clearly that's not the case. You can make it go a lot further if you design and deploy the network in a certain way. But you have to think about the network and the user equipment to make this work. So last week, Casa Systems announced a new product to market that we call the Aurus AI. We are taking advantage of this high power QTM527 high power antenna modules. It provides a very focused beam, it provides the long range coverage, and it provides that fixed wireless access performance that we think is necessary to enable the market. But in order to take into account the rapidly evolving network and new GNOBs being installed and reflections and the seasons changing, we have a platform that puts that high power solution onto a complete 360-degree steerable solution. So this device can be now future-proof for a rapidly evolving network. It can self-align, it can self-steer, and from an installation perspective, all that needs to happen is a cable needs to be run and the device needs to be installed safely on a location on the home. So we think that this type of solution really is the future for mmWave high power. We know the high power gives you the range and it gives you the performance, but it is quite limited in terms of the directionality of the beam, and the Casa steerability really solved that last limitation of the solution. So it's quite a elegant industrial design. The solution we have here pictured is for an outdoor solution. We're doing a lot of testing on the same solution for indoor as well. There are some challenges with the indoor that, as I mentioned, the location of the unit inside the home, needing to be near a window or near a door, really is a limiting factor from our testing so far. So we think there's a little bit more work required to really enable the self-installed use case. So at the moment, Casa are launching the optimized outdoor solution, and it's really quite a number of features in there that we're optimizing for the total cost of ownership for the end operator and the end user. Last but not least, just to take a bit of a step back onto what Casa Systems is about, and I know this is a technology webinar, so I don't want to dwell on the sales piece too often for too long, but the Casa Systems story really is an end-to-end story. We are readying a lot of our service provider customers for a disruptive service. On the right-hand side, we have our fully virtualized Axiom 5G converged core with a very efficient and a very both power and performance efficient virtualized 5G core. We have a 4G and a 5G RAN portfolio, particularly with a focus on small cells. And we move across to the left-hand side where we have the Access Devices team really focusing on a fixed wireless access story. Our ecosystem now has a number of FR1 sub-6 solutions, indoor and outdoor, and we just last week launched our Aurus AI mmWave high power FR2 solution, which is at the moment an outdoor solution. So it's quite innovative having the UE all the way through to the radio and through to the 5G core. We believe that this story is a really good story for those private 5G use cases that are coming to the market, but also for many of our service provider telco customers as well, who are looking to create some disruptive and new services to the market. So I'd like to thank everyone for their time today. Hopefully the message that I've been putting through is that the mmWave solutions are now coming to market and are working. Our development shows that it is performing better and quite unexpectedly, getting better range than many people expected. We're getting fiber type speeds, all done via wirelessly. And so my postulation for today is that while 5G's had a lot of press, it's actually 5G mmWave that's going to be broadband's next major disruptive technology. And it's going to be a complement to fiber or possibly an overlay to fiber in certain areas, depending on build out. So to take advantage, you can either join this mmWave disruption or you can potentially be disrupted yourself. I'd like to thank everyone for the time, and I'll hand back to Kevin, who's going to moderate for some questions.
Actually, Steve, I think this is Ian. I'll do the questions with you. That's right.
Oh, thanks, mate.
We've had several come in, actually. Again, for the audience, if you do have questions, if you look over on the left-hand side of the panel there, you'll see a Q&A tab. It says Q&A speakers handouts. Click on the Q&A. You can type in the question at the bottom there. We do have several. I'm going to start with one here. And actually, this is a good question. I'm going to pull you back to this slide here. Your long-range performance here, the throughput you were seeing at the different speeds. And it was something I noticed as well, but I'll read the question here. What made it possible to get higher download throughput from 3.3 to 3.8 kilometers compared to the 2.7 to 3.3? I'll extend that question and say, you said going out to about 5 kilometers. Do you see the floor do you see a floor in that throughput, or do you see it just going lower and lower? What sort of performance do you see? But why that little bump?
Yeah, the little bump's really an artifact of testing. It's only one data point. The data point of 3.3 kilometers was just a little bit low. It's kind of within the noise floor and the noise and measurement errors. It wasn't actually really a performance lift. It was just the 3.3 was a little bit low, and that could have been even down to, humidity at the time of the day, or I'm guessing here completely. It's kind of within the noise error bars, I think, of the throughput limits. A lot of this equipment and a lot of this testing was done with very, very early equipment. We were even struggling at some points to get the downlink performance to work because of back-end problems of, backhaul from the cell. So we were really citing the limits of what the whole ecosystem there. So I think if we took a lot more data points and ran it over, more measurements, I think we'd see that curve really even out into a more linear drop. In terms of your question about the 5 kilometers, we are still seeing that performance well above half a gig, so well above 500. The limitation is not so much the throughput performance. The limitation becomes a real time performance and the cycle time for the timing of getting a transmission out from the G-node bay and the acknowledgement coming back from the user equipment. That time of the round trip, that becomes the real critical factor here that was quite hard to design around. So we were still seeing well over 550 megabits a second, even out to 5 kilometers. But the timing advance becomes our problem and things drop out at that point.
Okay, all right. That's still pretty impressive, though. 500 megs at 5 kilometers.
Provided there's nothing in the way, just to be very clear. There's got to be nothing between the G-node B. It is a genuine line of sight test to get these types of distances. Yeah. I'm just thinking in my house, you would still exceed the speeds I get today on my wired broadband. So I think you could have line of sight as well. Okay, another question here, and again, something that occurred to me as well is, and I'll read this, will long-range millimeter wave recent achievements, the 3.8 kilometers here we're showing, accelerate the standalone deployments without the uplink on the lower bands? Is the pure millimeter wave SA completely without the lower bands? Is that practical from your view? So I guess the question, the two-part question here. One is this long-range performance, is it both downlink and uplink that you're getting these distances? And secondly, or is the uplink on the lower bands? Yeah, that's a really perceptive question. So this testing we did was pure downlink testing only. We didn't test uplink. In fact, the cells that we were testing on, we had to do a bunch of special upgrades to even get us these type of backhaul speeds to the cell. And they were optimized for downlink and not for uplink. So in fact, we don't have the data points yet for uplink performance. We don't yet have a configuration that allowed us to test it. What I can say is that we did have uplink, and it wasn't like all of the uplink was occurring in the lower bands as the question was put through. There was uplink happening, and the advantages we get from the high power millimeter wave actually are quite uplink focused. I talked about where's my slide here for here. So this high power 44 dBmi is actually an uplink power parameter that I'm talking about here. We have to enable the uplink to be able to do the acknowledgements and all those things. So we do have a full uplink performance. We haven't run the tests yet we do envisage that the uplink will work, and it then generally becomes uplink constrained, but I don't see any reason why we won't be able to have uplink work on the same distances that we saw here on the downlink graph. You won't have the same speeds because the power differential is quite different, but you still will have good performance, but we don't yet have the measurements because we haven't yet had a live cell that is configured correctly for us to test against. So I think that's going to be a watch this space for us to be able to give you those results. But I do envisage that pure SA mode will be possible, provided you are using the high power transceivers. I don't really think the low power transceivers are going to work very well at all.
Right. So just to be clear on this diagram, because I'd missed that, I kind of read it the traditional way from tower down to home, but actually on this, you're showing the 44 dBm high power is actually on the home for the uplink back to the tower, right?
Yeah, correct. I'm sorry if I wasn't clear on that. These are transmit from the UE power parameters.
Okay, that's good. Yeah, good.
Yeah.
Okay. All right. Another question here. I don't know if you can talk to this one at all, but what are you seeing in terms of density for suburban, urban use cases in terms of number of users per kilometer squared? I know you've got some topographical diagrams here, and that's been much talked about in the past for fixed wireless. How does this high power model change that from your perspective?
Yeah, I haven't got any of the numbers in front of me. I'm sorry, I can't give you any kind of link budget type numbers. But what we are seeing is that, I talked about this long range stuff here being a number of kilometres long. That is a line of sight type solution. It's useful for a rural or suburban use case. But for the urban type high density environment, what we're going for isn't so much getting to 5 kilometres, but getting to the point where reflections can be effective and a signal can make its way to inside the home. So the cell parameters, the cell radiuses will be a lot smaller, maybe in the kilometre type range or 1.5, which is okay actually for the urban suburban areas. But because you're running the high power UE, you can take advantage of the reflection type behaviours that the device has. So we do believe, and from the testing we're doing, that this standard urban and suburban density footprints are very realisable, but much more doable using these high power transceivers because you can't plan for the link path you're going to take because it bounces off things you won't expect. But the fact that you've got a higher power solution with not only the higher transmit power, but also the higher antenna gain, which gives you much better receive sensitivity as well. It's two-directional, these high power solutions. So the receive sensitivity is a hell of a lot higher as well, and the transmit power gives you a better chance of making use of those reflections, which you can't plan for, and installer sometimes can't even work out. But if you have an autonomous UE that can take advantage of the different paths, the signal may find a way, provided you give it as much chance as possible. So we do believe it's relevant for standard high density and urban density use cases.
Yeah, and I've actually heard this from operators who deployed millimeter wave is it doesn't bounce off some things they were expecting it to bounce off, but it does bounce off other things they weren't expecting a lot of reflection from. They've just kind of had to see how it goes, right? So there's another question kind of related to this that we had as well, Steve. And firstly, the speaker said, great presentation, by the way. But what are your thoughts on using a wireless mesh from the fixed wireless access CPE edge point? So I guess talking about a high power link to, and then a mesh area in the immediate local area.
Yeah, so I mean, Wi-Fi mesh has a definite role to play. And in fact, if I was to show you some more detailed slides about our customer presentations when we go in front of operators and I talk to them about these solutions, I will often say, use 5G to get to the side of the house and then use Wi-Fi mesh to get through the house in terms of dispersing the signal through all the bedrooms and living rooms inside the house. So I think the two technologies, when paired together, actually solve the problem. Without the Wi-Fi mesh 5G fixed wireless really struggles to find a way unless you're talking about lighting up maybe an enterprise and that's all Ethernet cable. Without the Wi-Fi mesh, it becomes very hard to get the signal through the home.
Right. Okay. One more question on the test, and then I've got one last question. We'll wrap up. And I think you said this somewhere, but I want to make sure. And the question was, what were the frequency bands and channel sizes used for the long range test in Australia? Yeah. Yeah.
So I don't have the actual channel number in front of me, but I can tell you it was in the 28 gig space.
Okay.
And I can tell you that this test was run with 4 component carriers. So we were using 400 megahertz for this test. We hadn't yet got the 800 megahertz channel 8 carrier working. We're seeing that starting to work now on the high power. So haven't got that data yet. But this was 4 component carriers, 400 megahertz in the 28 gig space.
Okay. All right, great. So 2 last questions for you. First one, does the RSAI have elevation steerable capability? I think in your diagram you're showing radial, right? What about elevation as well? Yep.
Yeah, so the answer is yes, but to a lesser extent. So the high power transceivers, the QTM527s, have an element of active beam steering built into them. There's an array of these antennas. They're reasonably expensive, these antennas, and you don't want to have a lot of them built around the perimeter of your device because you'd end up with a device that costs thousands and thousands of dollars because the antennas are so expensive. So we have 4 of these units, which provides beam steering of around, it's a little bit more complicated than this, but it's around 20 to 25 degrees left to right active beam steering and up and down beam steering. So you do have elevation beam steering of around about plus or minus 20 degrees, which is actually enough for normal tilt type adjustments. Then we have the mechanical steering, which takes the platform and gives you 360 degrees on all of that. But that's only the horizontal and mechanical steer.
Yep. Okay, good. And for those people, we did have a few more questions. For those that we didn't get to, we'll make sure we get them to Steve at the end to follow up with. So the last question is, obviously we're getting towards the end here of 2020. I think most people will be glad to see the back of this one. But you talked a lot about in your presentation about looking forward and the developments that you see coming. So what do you see as from your perspective? Obviously you're in the middle of all this, but what do you see as the major drivers of disruption for millimeter wave? Let's take it out to let's say 2022. What do you see is coming?
Yeah. So I think the big one, and there's been some questions on this today, which tells me that people are very interested in this, but the big one for me is a few things. One is a standalone millimeter wave. I think that is when we're going to see a lot of really interesting solutions come to market. I know it's very hard for disruptive type services to come in when you're looking at a non-standalone millimeter wave solution. I had a slide earlier which talked about NSA versus SA, and it's very hard for anyone but the incumbents to do anything but NSA because you need lots of channels and spectrum allocated and you need infrastructure, and it's very tricky. But once standalone features become really working and available for millimeter wave, I think we're going to see some really innovative solutions, more than just enhanced mobile broadband fixed wireless. I think we're going to see some really cool type devices. So I think that's going to be quite a disruptive feature once it's available and readily available, and that's going to be end of 22, end of 21, early 22, I reckon, before that's ready for prime time. The other thing I think that's going to be really cool is this third one here I've got on the screen, which is the private 5G enterprise/industrial type solutions. And people have been talking about private 4G and private 5G for many years, and it's forecast to be the next big thing. I really think with 5G and with things like Release 17 features coming through, I think we will finally start to see actual deployments of enterprise and private 5G. And I think we're going to see them come to market in a lot of unexpected ways. I think we're going to see some come through traditional telcos, but also some coming through traditional, what I would call IT services and IT players. And I think we're going to see some really interesting virtualized 5G cores on market, coming through IT players and enterprise channels to market that are going to create some really unique solutions. So that's where I think a lot of disruption is going to come over the next few years.
Okay, great. Well, Steve, thanks very much. Just a reminder, for those still on, Steve Collins is Senior VP of Access Devices for Casa Systems. My name is Ian Gillett from IGR, and I'll pass back to you, Kevin, to wrap us up.
Great. Thanks, Ian. Love seeing so many great questions there. For those of you know in the audience, we actually had a few dozen questions we weren't able to get to due to all the interest. Obviously, 5G mmWave is a pretty big topic. So thank you for attending this Fierce Wireless webinar. That being said, I'd like to thank our speakers for participating and Casa Systems for sponsoring today's event. And last but not least, please note that this webinar has been recorded. You will be able to access the recording within 24 hours using the same audience link that was sent to you earlier. So thank you again for joining, and we look forward to seeing you at future events.